morning, everyone. Today we delve into the fascinating world of organic chemistry, focusing on a powerful synthetic tool known as Stille reaction. The Stille reaction, named after John Kenneth Stille, is a powerful and versatile palladium catalyzed carbon carbon bond forming reaction between organohalides and organostenons. Right. So, basic scheme of the reaction is what we will see is organohalide reacts with organostenon in presence of the palladium catalyst to give a cross-coupled product like this. Here, the catalyst is tetrakase triphenylphosphine palladium. However, in the direct coupling like this, the active catalytic species is assumed to be palladium EPS32 instead of this. That is bis triphenylphosphine palladium. Alright. So, in 1978, John Stille proposed a mechanism for this Stille reaction, but before diving into the intricate details of the mechanism, let's take a step back to appreciate the historical journey of the Stille reaction and its development. The Stille reaction builds upon the legacy of brilliant minds like Richard Hack and Akira Suzuki. These two legends laid the foundation and groundwork of the cross-coupling reactions. Now, what happens? Let me tell you something. At the same time, when Stille proposed the mechanism, in the world of natural products, scientists and chemists were studying this compound called rapamycin. This particular compound is alone attracted so much attention because of its unique properties. First of all, this compound was indigenous to the soil of Easter Island. Easter Island. Must have heard of this place. Right. This compound exhibited several impressive properties, like, for example, it was a powerful immunosuppressive agent. Along with its excellent cytotoxic properties and its antibiotic behavior. Due to these properties, rapamycin was used in organ transplant. And somehow, our Stille reaction found its application in the synthesis of this compound rapamycin. This underlines the importance of the synthetic pathways and the importance of Stille reaction in real world. Now, we shall discuss the intricate dance of atoms that constitute the mechanism of Stille reaction. At its core, the Stille reaction involves the coupling of organostennin with organohalides, and the magic happens as the palladium facilitates the oxidative addition of alkyl halide, oxidative addition of alkyl halide or organohalide, to be more precise, organohalide, and this palladium shuttles between different oxidation states such as palladium 0 to palladium 2, orchestrating the delicate dance of carbon-carbon bond formation. Followed by this step, this was the first step, oxidative addition in the mechanism of a Stille reaction. The second step involves transmetallation, which is nothing but the transfer of a ligand from one metal to another. Alright. The third step involves trans to cis fascile isomerization. And the final step, which gives us our desired coupled product and also releases the initial catalyst, is reductive elimination. This is nothing, we will see. The first step, oxidative addition, what happens here? We can see from the name, oxidative and addition. So there is happening oxidation and addition at the same time. How does it happen? Let's see. So this is our organohalide right here, and it reacts with here our catalyst to give something like this. Alright, so here we can see the coordination number here was 2, here coordination number increased by 2 and became 4. Also, oxidation state here 0, oxidation state here increased by 2, and now it is in plus 2 oxidation state. So, transmetallation we discussed is the transfer of one ligand from one metal to another. We will see in the next few minutes in much more details these two steps. Now, the reductive elimination is just the opposite of oxidative addition. Reduction takes place, also elimination at the same time. So, here what is happening is coordination number will decrease by 2 of palladium, also the oxidation state will again decrease by 2. Okay. So now let's dive deep into the mechanism, understand it. Correct. So our initial starting of catalyst and complex is this, and the first step involves oxidative addition of to give us the next step is transmetallation. Now here, this R group, for simplicity, I am taking the R group to be methyl. However, the reaction does not actually depend upon this R group. However, these two R groups that are to be coupled, this could be aride, allyl, or alkynyl. Alright. So here we are. So you get something like this. So we are saying that this product is in trans fashion. So what happens next is trans to cis isomerization. Alright. So this step like this, and in the final step it regenerates the initial catalyst, also giving us our required coupling product. This step is known as reductive elimination. So this was the Stille reaction for you, and now we will move on to discuss some advantages and disadvantages of Stille reaction quickly. So let's discuss some advantages first. The advantages of Stille reactions are advantages first that organotin reagents are air and moisture stable. Also, they are chemoselective. This reaction is chemoselective. Organotin reagents are chemoselective. Third, they provide good yield and uses milder reaction condition. Alright. Now, let's move on to some disadvantages also. First, the major disadvantage is the toxicity. Toxicity associated with the organotin reagents. Also, high cost of palladium makes the reaction quite costly or economically unfeasible for industrial and large scale production. That was our review of the Stille reaction. Thank you for being with me, and that's all for today's lecture.